Hello class. In previous videos, we talked about constitutional isomers. I want to take a step back and just analyze the word isomer and what that means. Isomer is composed of two words from Greek, isos and meros. And when you combine those two words together, they simply mean made of the same parts. So you remember when we had a chemical formula that looked like this, and we could draw the molecule that looks like that, or we could have drawn it like this, 1, 2, 3, 4. And these guys are called isomers of one another because each one has 4 carbons, 10 hydrogens. 1, 2, 3, 4, 4 carbons, 10 hydrogens. They're isomers of one another. Now, I said that these two right here are called constitutional isomers. Constitutional isomers are molecules that have the same molecular formula but different connectivity. You can see here that it's a zigzag versus this structure right here. The connectivity of the atoms is different. And so what we are going to focus our attention on is the fact that we're going to have two different types of isomers that we want to look at. We have constitutional isomers and then we have stereoisomers. And we've briefly looked at constitutional isomers in previous videos. But if we could put a definition to constitutional isomers, it would simply be molecules that have the same chemical formula but different connectivity. Stereoisomers, on the other hand, have the same connectivity, same chemical formula, but different orientation in space. So what if I drew something like this? What if I had a chemical formula like this? Okay. And we draw the molecule like so. Okay. So there's a molecule. Now I'm going to draw another molecule in a different color. Let's not make that a wedge. Let's make that a dash. Now what we have here is two different molecules, but look at this. Carbon 1, 2, 3, 4. Carbons 1, 2, 3, 4. What do we see? We see the connectivity between these two molecules are exactly the same. The bromine atom is attached to carbon 2. Bromine, carbon 2. We have the same zigzag. All the hydrogens are attached to the same carbons. Everything matches when it comes to connectivity. The chemical formulas are the same. The connectivity is the same. But the spatial arrangement of these bromines are different because this bromine is a wedge, so it's sticking out of the board, and this is a dashed bromine, so it's sticking into the board. And so these two molecules are called stereoisomers of one another. These are stereoisomers because they have the same molecular formula, same connectivity. It's just the spatial arrangement of the atoms is different. Now we could take a look at cyclohexane rings. Recall from previous videos where we could look at a cyclohexane, a disubstituted cyclohexane ring like this. So we have two methyl groups there, but then we compare it to another molecule that looks like this. And if we want to put in our methyls, maybe let's do that. Here's our methyl groups. When you compare these two molecules, what you should be able to notice is that they have the same chemical formulas, same connectivity, just a different spatial orientation. So if we numbered them, we could say that's carbon 1, that's carbon 2, carbon 1, carbon 2. You can see all the connectivity is exactly the same. It's just we've switched out a wedge for a dash, and that's different spatial orientation. Now what we have going on here is when we look at the substituents, we can see that they are on the same side of the ring. They're both a wedge. Recall what we call that relationship when the substituents are on the same side of the cyclohexane ring. We call that cis. And then when they are on the opposite sides of the ring, what do we call that? We call that trans. Now we're going to now introduce looking at different stereoisomers when we look at alkenes. So let's take a look at butene. Okay, we have 4 carbons. So that is a butene. Now you could also look at butene like this. So let's draw that a little bit. It's bonded to the carbon, obviously. That bond right there doesn't go to the hydrogens, it goes to the carbon. Okay. Now, looking at what we've learned here, right, we can apply that same concept to alkenes. Look at that. What we're going to do is when we look at the alkene, let me see here. How do we want to talk about this here? So what you want to notice is when you have an alkene, just split it right down the middle, like that, okay? And then on one side of the ring, which group is the largest? A hydrogen or a methyl? Well, that's the largest group. Now do the same process on this side right here. And we can see the methyl group's larger than this hydrogen. And now we get rid of this imaginary line that we drew. And then we look at it from this perspective, from the horizontal perspective. And we ask ourselves, are the two largest groups on the same side or on the opposites? And they're on the same side, so that would be cis. You can do that same analysis for this one. We see that this one's the largest on the left side, and this one is the largest on the right side. And then we just look at above and below that double bond there, where are those two groups? And we can see that they are on opposite sides of one another. And so that makes that trans. So we can have cis alkenes and trans alkenes. And what's the relationship between these two? They're stereoisomers because they have the same molecular formulas, but different and same connectivity, just different orientation in space. So if we start these carbons right here, we can see that these star carbons have a methyl, a hydrogen, and a double bonded carbon. And then if you look from this direction, same thing, hydrogen, carbon, boom, boom. Same thing over here. If we start these carbons, we have this starred carbon right here has a methyl, a hydrogen, and a double bonded carbon. The connectivity is the same. It's just the spatial arrangement between these two alkenes is different. Now, one very important concept to understand here we have butane there versus this. Now, what's the difference? What's the relationship between these? Are they have the same molecular formula, same connectivity? Are they stereoisomers? They're not. They're conformers of one another. Remember how these guys right here have free bond rotation right there because they're single bonds? And so this conformer could rotate and look like this conformer right here. But when we have alkenes, what do they introduce here? What's introduced in an alkene is a double bond. And that double bond prevents rotation around this bond. That does not happen. There's no bond rotation for double bonds. None whatsoever. So these alkenes, they're stuck in their spatial orientation. That is always going to be cis. This is always going to be trans. They don't go back and forth. And when they don't go back and forth like that, they're going to be isomers of one another, and more specifically, stereoisomers in this case. Now, why can't there be free bond rotation right here? Well, what's going to happen is I'm going to take this molecule that's in the plane, okay, in the plane of the glass, I'm going to tip it 90 degrees. And so when I tip it 90 degrees, what I have is the methyl groups going into the board, okay? So I've just tipped it 90 degrees. And so to make my drawing to make it look a little bit better here, I'm going to just extend those out just a little bit wider, okay, like that. So they're sticking out. What we have here is a double bond, and that's because we have p orbitals, right? So I'm going to erase that double bond right there and represent it by the p orbitals here. And they have phases, right, like so. So the p orbitals here in pink are representing the double bond, the pi bond. Now, when this alkene is formed, you have a strong interaction right here. That's causing the double bond over here. And so if you rotate around this bond right here, what's going to happen? You're going to disrupt that interaction. Because if you take this carbon right here and rotate it, what are you going to do? That interaction between those two orbitals are going to be destroyed. And so it's not going to rotate because it's going to destroy that double bond. So they stay in place. Moral of the story, double bonds do not rotate. They cannot because of this orbital interaction right here. So let's take a look at this alkene here. And our job here is to classify this as cis or trans. How do we do it? Well, one good idea is to draw in the hydrogens that are not shown. Okay. And then, like I said, we go right down the middle of that double bond, right there. And then we circle which groups attached to this carbon are the largest. Hydrogen or the benzene ring. Now the pH stands for phenyl, which is also another way of saying when you have a benzene ring attached to something. Okay. So what we could do is represent this pH as the benzene ring. All right, so we could go look like this. So whenever you see a pH on a ring or on a molecule, it's talking about, so that would be, let's go like this, pH. Okay. Okay, now let's get back to our question here. Now that we understand exactly what the molecule looks like, we just have to circle the ones that are the largest here. On this carbon here, on the left side of that dotted green line, we see this ring is big, that's bigger than the hydrogen. And then on the right side of that green dotted line, we see the ethyl group is larger than the hydrogen. And then we just erase this line, and then we have it on this side right here, right down the double bond, and we just ask ourselves, which are the circles on the same side of the green line or on opposite sides? And we can see one's below the dotted line, this one's above the dotted line. So that makes this molecule trans. Okay. What do you think about a molecule that looks something like this? Like that. Okay. No, not like that. Let me redraw it here. We'll draw our double bond like that. Okay, like that. So this right here is called, so is this cis or trans? Well, we go through the same process. Okay, we draw in every piece. And now we go right down the middle there. And we can see a propyl is bigger than a methyl. But then we come to this carbon here, and we were like two hydrogens. How do we break the tie? We don't. So when you see alkenes that are di-substituted, and what do I mean by di-substituted? When we're looking at an alkene, we identify the two carbons that are at the double bonds right there in pink, and then we just count how many alkyl groups are directly attached to those pink carbons. And in this case, I see that there's 2 carbons. So that's 2, meaning di. So if I draw something like this, what is the substitution pattern for this guy? Well, there's the 2 carbons in pink. How many alkyl groups are directly attached? 1, 2, 3. So that's tri-substituted. And if we put on a 4th one, that's going to be called tetra-substituted. So we cover tetra, we cover tri, we cover di, and so you can already see what mono is going to look like, right? There. There's only one substitution, that methyl group right there. Okay. Let me double check something. I think the computer's acting up. Okay, now what we have here is a alkene that is tri-substituted. And so that simply means three groups attached to these double bonded carbons that are not hydrogens. So we can see here's a group, fluorine, the ethyl. So there's three groups that are not hydrogen. So we can call this alkene a tri-substituted alkene. Now our goal here for this tri-substituted alkene is how do we classify it as cis or trans? Well, let's follow the same procedures. Okay. Go down there. And now let's do the right side here. What we're doing is we're comparing the atomic size between the two groups. We have an oxygen versus a hydrogen. Which one's going to be larger? Which one's when you look at a periodic table, which one has the largest atomic mass? The oxygen does. So we circle that guy. And then we come to the left side. And now we are looking at, hey, a fluorine versus a carbon. So we have a fluorine and a carbon. And fluorines have a larger atomic mass. Okay? So we circle that right there. Okay? And now we can see that when we draw the horizontal line here, that both these groups are on the same side. So we would think, based off of what I've taught you up to this point, we'd call that cis. But when you look at that molecule and I say this is a cis alkene, and that's the only words that I use is cis alkene, how do you know that the fluorine and the OCH3 are cis instead of saying that this methyl, but what's the relationship between this ethyl and the OCH3? It's trans, right? So it's really ambiguous when I say this alkene is cis. What am I referring to? Am I referring to these two groups are cis? Or am I looking at what's the relationship between this ethyl and that? Well, that's trans. And so we can't really use cis and trans when the molecule or the alkene when it's tri or tetra substituted. So what we have to do is use a different way to classify this alkene. Okay? Now the way that we do this is the exact same idea. Okay? We go down there, we go to the left side, and we prioritize the groups. And we're prioritizing them just the way I showed you. Fluorine is larger than a carbon. We do it over here. Oxygen is larger than a hydrogen. Okay. Now, we look at it across the double bond right here. And we can see that the two groups that take priority due to their size, their atomic mass, they are on the same side. They're on the same side of that double bond. So what we do is we classify it as a Z. That is a Z alkene. And the way I like to remember it is Z stands for the same side. Just like that. Now let's go to this molecule on the right here and take a look at it here. So we'll do the same process. Let's use pink. We'll go here. We have a fluorine compared to a carbon that has a higher atomic mass. We have a hydrogen versus an O that it's a larger atomic mass, so that takes precedence. right there. Now what do we see? They are on opposite sides. And when they're on opposite sides, we call that a E alkene. And yes, this is corny, but that stands for opposite side. So we have the Z for the same side, and we have the E for the opposite side. And so we scrap the cis-trans classification when we have a tri or tetrasubstituted alkenes. Okay? So let's review isomers and then introduce some new things here. So we have our isomers, and this is just a flow chart on how you can classify molecules when you're looking at two different molecules here. So they're isomers. So we look at and ask a question, do they have the same connectivity? Okay? If they have the same if the answer is yes, if they have the same connectivity in the same molecular formula, then they are going to be called stereoisomers. Whereas if they have the same, if they don't have the same connectivity, but they have the same molecular formula, then they are called constitutional isomers. And we've spent time there. We've discussed stereoisomers, but now we can then take stereoisomers and expand on that. So we ask a question, do the stereoisomers, are they different by rotations about a single bonds? If yes, then they're called conformers. Remember when I had butane like this versus butane like that? There's rotation around that single bond. Okay? They look, if the connectivity is the same, okay, connectivity is the same between the two, same molecular formulas. So they're different between these two by the orientation in space. So that's by definition stereoisomers, right? Same connectivity, different orientation in space. But they're different by a single bond rotation, okay? And so what's the definition between those two? Is because I could take this guy and rotate it and make it look exactly like this one, right? So these two descriptions of the molecule are called conformers. And we've talked about that. But if the answer is no, they're not different by a single bond, by rotation of a single bond, then we have configurational isomers. Okay? And this is where we are going, this is introducing the new topic that we are going to discuss. In configurational isomers, okay, we then ask another question. Are they a mirror image? Now we haven't talked about that yet. Okay? But if you ask the question, if they're mirror images, when you're looking at two molecules, if the answer is yes, then the relationship between those configural isomers is called an enantiomer. And I've ran out of board space, so if I start writing it below this pink arrow, you won't see it. So I'm just going to write it over here so you can see what the word looks like, but make sure you understand that it goes below this pink arrow, okay? And the word is an enantiomer. So that word goes right there. If it is a mirror image, then we have an enantiomer. If there's no mirror image, then we call it a diastereomer. Let me double check if I spelt that one right. I doubt I did. I just added an I for some reason. Diastereomer. So that would be below this pink arrow right there, okay? So now you can see here what we're doing is we're looking at stereoisomers. We've already discussed conformers, and now we are now going to look at configurational isomers. And then we look at those, and we can break them down even further to enantiomers and diastereomers. So this is where we are now going to jump into and understand what's going on, okay? Okay, let's talk about stereoisomerisms. Now, in order to fully grasp this concept, we need to understand mirrors. We're going to be talking about taking molecules and put them in front of a mirror, and do you see the reflection? Okay? So let's just pretend you put up a mirror in the bathroom and you're looking right at the mirror. And you take your hand and put it up to the mirror. Okay? So you see the back of your hand, but when you look into the mirror, what do you see? So if I put up my right hand, the reflection in the mirror looks like my left hand. All right? So let's do that exercise. Go into the mirror, and you can put up your right hand, but the reflection looks like your left hand. And so if I take my right hand, put it up in the mirror, what I'm seeing is my left hand is a reflection of that. Okay? You can see that my left and right hand. So if I take that reflection, okay, and I rotate it this way, now I'm looking at the mirror is in between right here. So now I'm out of the plane of the glass, okay? And so right in the middle of me is this mirror, and I'm going to put my right hand there. And so what am I going to see in the mirror over here? It looks like my left hand, right? Okay. So that's how we're going to visualize these molecules. You can start by just looking at the mirror in the plane, and then you have to pull out of the mirror, okay, and go like this. All right. So if this is the mirror's in here, I got to rotate it. And now the mirror's in the middle of me, like that, okay? So let's say we take any shape. Let's say we take the letter A. Any object, any shape. And I take that object and put a mirror right there. So the dotted line is representing our mirror. What would the reflection of A look like on this side of the mirror? What would that reflection look like? It would be the reflection of it, right? And if I draw it exactly how I should, I want everything perfect. Okay, so just envision a perfectly drawn A. And then we would have a perfect reflection on this side. Okay? So this is our real object. This is the reflection. Because that's what the mirror is showing. Okay? Here's our real object, here's the reflection. Now, we can see they look exactly the same, right? Now, let's just put our fingers together and do a magic trick, okay? And we can go abracadabra, boom. We're going to turn this reflection into an actual object. All right, real. So now we've just like multiplied it, just boom. We've taken this object, looked at the reflection, and then cast a spell in that reflection, said become real. So now we've erased our mirror. So now we have two real objects, okay? And I'm going to put a little asterisk on this one here because this one is now an actual object, but it came from the reflection of this guy. And now I ask myself a very important question. Is this molecule, or sorry, this object superimposable? Not that way. Superimposable. There we go. Now, an object is superimposable when you can pick it up and put it directly on top of the original, and they match perfectly in every way. So you could see that I could pick up this one on here, take it out of the board, and put it directly on top. It's perfectly superimposable. And when objects are completely superimposable, or when molecules are completely superimposable, the molecule or object is achiral. An achiral molecule is something that is superimposable. All right. So what we can say about this object right here, ignoring this one, just totally ignore that one. If we're just looking at this guy right here, we could classify this object as an achiral object, because if I took this real object and pretended there's a mirror, did a reflection, and then I took this reflection, magical powers, make it real, grab it, and then put it over, and if it superimposes perfectly, then I know it's achiral. So this molecule right here is I keep saying molecule, object, is achiral. So if I do that same analysis with an actual molecule, okay, we're going to do that same thing. So what if I take a molecule like this, right there, draw a hydrogen there, draw another hydrogen, and then do a Br right there. I want to know if I can classify this molecule as achiral. So what we do is the same process that I did with that letter A. I pretend there's a mirror. And now I need to do a reflection. So that reflection is going to look like this. That hydrogen's there, so it reflects like that. And then this hydrogen is a wedge. And that's an OH. And then the bromine goes like that. So this is the reflection of that. Another way that you can figure out how to draw the reflection is just imagine this mirror is actually a crease in the page in the book. It's the spine of a book, and you can take this page and fold them upon each other, and you'll see that they're going to be the same. So that's how I draw my mirror images. Okay? Now, we take this reflected molecule, do our magic, make it a real molecule now. Now you're going to take this molecule, the way it's drawn here, pull it out of the board, and will it superimpose perfectly? Well, when we look at it, the OH and the hydrogen right here, the wedged hydrogen, when I take it, do you see how they go perfectly on top of each other? But this dash bromine is on top of this hydrogen, and this hydrogen is on top of this dashed bromine. So you see they don't really work. They're not superimposable. But you have to be very careful here, because these molecules right here don't stay in place. They can rotate in three-dimensional space. So what I could do right here, okay, is we could take this molecule and we can rotate it. And if we can rotate it, we will see if it's superimposable or not. Okay? So what we're going to do is take this molecule and rotate it a bit and see if we can get this reflected piece to superimpose. Now what's going to happen is you're going to take the reflected molecule and you're going to rotate it in any way you want to see if it can superimpose perfectly. And you can take this molecule, take like this oxygen atom and twist it. And you can twist this molecule around and it's going to twist in such a way that it will superimpose perfectly on here. Now, how many of you are watching this video going, what? How can we take this and all the bonds match perfectly, all the wedges and the dashes? Well, if you take this molecule and spin it, this hydrogen bond right here, okay, will become the wedge. This one will become the line in the plane. And this one right here is going to just stay as a dash. If you can't see it visually, that is okay. This is a very visual concept. So what I highly recommend that you do is go to your organic chemistry kit and build this molecule. Look at it and draw everything exactly the same, and then make a second molecule like this and draw it perfectly how it's drawn here. And then take the molecules and rotate them in three-dimensional space and see if they're superimposable. I can promise you that these two molecules are superimposable upon one another. And because they're superimposable, that makes this molecule right here achiral. Okay. Now the next idea is when you have an object or a molecule that is non-superimposable. So we will just change this word here. Let's use the same color though. Non-superimposable. When any object or molecule is non-superimposable, then we have what's called a chiral molecule. So let's just look at an example real quickly with an object here. All right. So here's our mirror plane. Here's our mirror. Okay. Now if I take my left hand right here, what's going to be the mirror? It's going to be my right hand. Okay. Now when I take this hand right here, which is the mirror image of this hand, and I take this hand right here, and can I superimpose it? Now look at this. Can I superimpose it? Do you see what's wrong? The thumbs, all the fingers are in the wrong space. My pointer finger is overlaid with this pinky finger, and my thumbs are on opposite sides. But what if I take it like this? Well, that's not superimposable because, look, the back of my hand on this hand is facing you, and the back of my hand on the other hand is facing away from you. It's not perfectly superimposable. What's going on here is that's a mirror image. But when I take that mirror image and try to superimpose it, nothing matches up. It's not perfectly superimposable. Because when I want to superimpose my hands, I want my palms, both of them facing you. Not superimposable. But if I flip one, now the back of my hand's facing you and my palm's here, and it's not superimposable. It's not perfectly superimposable. And so that means my hands are chiral. They're chiral objects. You've experienced chiral objects before. Try putting your right shoe on your left foot. Does it feel comfortable? No. Because your shoes are chiral, and so are your feet. So you can't take a chiral left foot and put it into a chiral right shoe. It does not work. So let's apply this to molecules now. Okay. So what molecule do I want to draw here? We'll draw a hydrogen there. We'll draw a wedged methyl. And let's do a bromine. Now we want to figure out, is this molecule chiral or achiral? We do the same process here. We draw a mirror, and we draw that reflection. And how do we draw that reflection? You start with the carbons. Just draw the carbon in the center, and then the reflection. We have our wedge CH3. And that's the reflection. And I know I've done the reflection correctly is if I treat these as pages and fold them, and they lay on top of each other. Okay, so here is the reflection of our real molecule. We take this reflection, zap it with our magic powers, and say, okay, now we're going to make you real. And now we'll take this reflected molecule out, and can we superimpose it? Well, our OH and our methyl superimpose very nicely, but then you can see these two do not. Now, if I take this molecule here and rotate it, okay, to get the bromines to align, and I rotate it, watch what happens. Okay, I'm going to rotate. The bromine's going to go here. So now I'm feeling pretty good, right? Because now the OH and the bromine, I take it. We can see that the carbon, everything matches, superimposes perfectly. But look at what happens when I take this molecule and rotate it. The CH3 goes there, and the hydrogen goes there. Okay? What has happened? Can I take this? So I've taken the reflected molecule and spun it to look like this. Now can I take this and superimpose it on this guy? Well, the bromines and OHs and carbons work, but now the hydrogens and the methyl don't. And so I keep spinning and I keep trying this out, but ultimately what happens is it does not superimpose. It can't. It's non-superimposable. And so when we have the reflected molecule that's non-superimposable to the original, that molecule right here is going to be chiral. Now, when you have molecules with a carbon, and there's 4 different groups, listen to those words, 4 different groups, the molecule is chiral. So we have a carbon here, we have a hydrogen, hydroxyl, a methyl, and a bromine. There are 4 different groups. So that's going to make this molecule chiral. So let's take a look at what if I drew another molecule like this. CH3. Let's see, ethyl, something like that. But that would be what? A dash. Okay? When I take a look at this, I can see a methyl carbon, an ethyl carbon, and a propyl. But when we take a look at the groups themselves, you see that that's a hydrogen, that's a methyl, that's an ethyl, and that's a isopropyl. There are 4 different groups. So that makes that molecule chiral. But pay attention to the first molecule that I showed you. What did it look like? I think it looked like this. And this molecule is achiral because we have a OH and a bromine. They're different, but then these guys right here, they're two hydrogens. Those are the same. So that molecule is achiral. Now this analysis that I'm sharing with you, we're going to just say this applies to molecules with one carbon for right now, okay? If you start adding more carbons, things get a little bit more complicated, and we will discuss that later. We will get to more complicated molecules. But for right now, if you have one carbon and there's 4 different groups, your molecule is going to be chiral. If your molecule has more than one carbon, things get a little bit more difficult. All right? So what did I want to say here? When you have a carbon with 4 different groups around them, we can say that the carbon itself, okay, this carbon itself is a stereocenter. That carbon right there is a stereocenter. Your textbook talks about that is a chiral center. That's not technically correct. That's a wrong way of just saying it. Because when you look at my hands, my hand is chiral. Where's the chiral center? There's no, it's not. There's no chiral center. The whole hand is just chiral. Well, that's chiral. You don't say, hey, there's the chiral center. No, the whole molecule's chiral, but the carbon there is the stereocenter. Okay? So when we take a look at a molecule here, and I know we're short on time now, but I want to get this put in real quick here. One last little thing. Let's say we have a molecule that looks like this. Now we're adding more carbons, okay? Okay. And then let's do where are the stereocenters in this molecule? And the way you do that is you just look at every carbon and count how many different groups are attached. So here's a carbon. There's 3 hydrogens. So that's not 4 different groups. So we move on. That is not a stereocenter. Come here. We see, here's a carbon here, and it has a methyl group, a bromine, a hydrogen that's not shown, and then this whole piece right there. Do you see how each group, a methyl, a bromine, and hydrogen, and this big blob is totally different? They're all different. So that makes that a stereocenter. If we continue on, is this a stereocenter? No, because it has 2 hydrogens. Is that a stereocenter? No, it has 2 hydrogens. Is that a stereocenter? No, it has 3 hydrogens. What about this hydrogen? Or sorry, what about this carbon? Well, it has a wedged hydrogen there. So 1, 2. It's directly attached to this methyl. And then this carbon is directly attached to this piece. So when we're looking at, so that makes this guy a stereocenter. And when we're trying to find stereocenters in a molecule, we're just looking at a carbon and asking the 4 groups that are directly attached to that carbon, are they different? And so we do have, hey, that's a stereocenter, that's a stereocenter. Now, when you have more than one carbon, that's a stereocenter, the molecule may be chiral or it may be achiral. We are going to need some other skill sets to determine if the molecule is chiral or not. Just because it has stereocenters does not make it chiral all the time. It does most of the time, but there's some exceptions to that. Okay, so that's a good place to stop. Nope, wrong button.